Today we're going to talk about how much error there is when we use a Taylor series to approximate a function. So remember that a Taylor series is just an approximation for another function. So we're going to determine how much error there is when we use that. All right, I would strongly suggest that you pause this video and read this entire front page. There are a whole lot of words on this page, but it's a really good summary of everything that we're doing. I'm not going to read it to you, so I'd like for you to read it on your own, and then I will highlight the major points of it. All right, so pause the video and read this first page, please. Okay, so hopefully you've read this first page. All right, so what we're going to start with is, or what's given is that f of x is equal to an infinite Taylor series in x. Now, we have not created an infinite Taylor series yet. We will in the future. Right now, we've just created, say, the first 5 terms or the 4th degree Taylor polynomial or something like that. So we haven't done an infinite one, but for our purposes right now, f of x is going to represent an infinite Taylor series. And an infinite Taylor series exactly matches the f of x. If we have a finite Taylor series, like a few terms, then that's an approximation for f of x. But an infinite Taylor series is an exact replica of what f of x is. So a partial sum is the sum of the first few terms of the series, and we're going to call this p of x. This is what we've been doing and what we've been creating. The tail is the rest of the terms of the series after a partial sum. So that's what we've left off. So the remainder is the number that you get by adding all the terms in the tail, and we're going to call this r of x. All right, so therefore f of x, the original series, would equal p of x plus r of x. So f of x, the original function, is going to equal the finite number of terms that we create in the Taylor series plus the remaining terms that would make it infinite. So the error is the error that you make in assuming that f of x is equal to p of x. And it's not, because p of x is just an approximation. So the error is the same number as the remainder. So that's kind of the same thing. You've got to get that through your head. And then an error bound is a number known to be greater than the absolute value of the remainder. It's basically how far you can go in either direction of your approximation and still be a reasonable answer. Something that you're familiar with for a convergent alternating series, then the absolute value of the first term of the tail, or the first neglected term is what we called it, that's the error bound. Okay, but go away from alternating series and we're going to talk about Taylor series. All right, so Taylor's theorem, this looks scary, but it's really very familiar to you. Basically, f of x is this Taylor series right here, but instead of what you learned yesterday with the plus dot dot dot, meaning it goes on forever and ever, they're saying that we're going to write out a few finite terms, and then we're going to call the rest of this, or the tail, the remainder. So they're saying that f of x is exactly equal to the first few finite terms plus the tail, or all the other terms that we're going to call the remainder. And the remainder is given by this. And what this means, this f of n plus 1, that means like the next derivative. Like f prime is the first derivative, f double prime is the second derivative, f to the n is the nth derivative. So this is the next derivative at some number z divided by n plus 1 times x minus c to the n plus 1. That is the value of all of the remaining terms. And z is some number that's between x and c. Now remember, c is where you're centered, and then x is the value that you're plugging into the function to approximate. So basically the remainder is exactly equal to this next derivative evaluated at some number z that's between x and c, and then divided by n plus 1 factorial times x minus c to the n plus 1. It's in keeping with this exact, with this formula right here. Now, the problem is that there's no way to really find this magic z. So that brings up what this guy named Lagrange figured out, And Lagrange figured out that if we just take the maximum value of this next derivative between x and c, so z is somewhere between x and c, so we're just going to find the maximum of that next derivative between c and x, then that number is going to be either greater than or equal to f of n plus 1 at z. So by doing this, what we've done is we're overestimating our error, but that'll give us this error bound. So this is the formula that you need to know. Right here is that your error is less than or equal to the maximum of your next derivative between c and x divided by n plus 1 factorial over x minus c to the n plus 1. Okay. This part right here, you'll hear me refer to as big M. Okay, so big M is the maximum of that next derivative between your centering point and that x value that we're plugging into f of x for the approximation. All right, the AP test uses the following notation for error, and it's essentially the way that they represent the error, that the error is the same thing as the remainder, but the remainder is the value of the actual value of f of x minus your approximating value. And that makes sense from what we started with back here, and that f of x is equal to the approximation plus the remainder. So they've just essentially solved this equation for the remainder and say that the remainder is the same thing as f of x minus p of x. And oftentimes on the AP exam, they will ask you to find the absolute value of f of x minus p of x, and that's just their way of saying find the remainder or find the error of this approximation. Okay, let's jump into working some examples. And all of these examples are examples that are often used or often come up on the AP exam. All right, so the function f has derivatives of all orders for all real numbers x, and then we're given the values of the first, second, and third derivatives at x equal 2. So write the third degree Taylor polynomial for f about x equal 2 and use it to approximate f of 2.3. All right, this is what you did yesterday, so we're just starting with what we did yesterday. Okay, so that remember to create each of the terms in the Taylor series, then we need to take the nth derivative at the centering point times x minus my center to the nth power all over n factorial. And that's just how I create each of my terms. Okay, so my Taylor series, and I'm going to do the third degree, so I'm going to call this P3 of x. You don't have to do that, but I just think it's nice to kind of keep it neat and to label it P3 of x. So we start with f of 2 because we're centered at x equal 2. So f of 2 is 6 plus the first derivative is 4 times x minus 2 to the first power plus the third derivative, the second derivative is negative 7. And I have to divide by 2 factorial times x minus 2 squared, and then plus the third derivative, which is 8, times x minus 2 cubed, divided by 3 factorial. Okay, so that's my third degree Taylor polynomial. Now, if I want to use it to approximate f of 2.3, then f of 2.3 is approximately P3 of 2.3. Do not write that f of 2.3 equals whatever we get for this decimal right here. Now, P3 of 2.3 is just P of x evaluated at x equals 2.3. And if you type that into your calculator, you get 6.921. To save time, I'm just going to tell you that. Now, whatever you do, do not write that f of 2.3 is equal to 6.921. Because it's not. F of 2.3 is approximately 6.921. So So the best way to write this is f of 2.3 is approximately equal to p of 2.3, and p of 2.3 is equal to 6.921. Okay, part B. The fourth derivative of f of x satisfies the inequality that the absolute value of the fourth derivative of x is less than or equal to 9 for all x in the closed interval between 2 and 2.3. Now when you first read that, you may be thinking, what the heck does that mean? But we're supposed to use this information to find the error bound in the approximation of f of 2.3 found in part A. So essentially, we're trying to find the error in this approximation that we used right there. Well, we know that our error, using either Taylor's theorem or Lagrange error, whatever you want to call it, it's all the same thing, is the maximum of my next derivative on the interval between x and c. Well, c is where it's centered, so I'm centered at 2, and then x is 2.3 because that's what I was plugging in to make my approximation. So it's on the interval between 2 and 2.3, and then times the difference between x and c, and it's the absolute value of the difference between x and c. So I always just take the bigger number minus the smaller number. So 2.3 minus 2 to the n plus 1 power, and then over n plus 1 factorial. Okay, so if we use the third degree Taylor polynomial to make this approximation, then our next derivative, or our next n power that we're going to use, is going to be the fourth power. So I need to find the maximum of the fourth derivative between 2 and 2.3. Well, that's what they're telling you this is right here. If the absolute value of that fourth derivative is always less than or equal to 9 between 2 and 2.3, then the maximum of that fourth derivative is 9. So our remainder, or our error, and here's a good notation for your error or your remainder. It's the remainder using the third degree to approximate when x is 2.3. So that remainder is equal to our error, and the error will be less than or equal to the maximum of our fourth derivative, which is 9, times the difference between 2.3 and 2, so that's 0.3, to the fourth power, over 4 factorial. And if you type that into your calculator, you get 0.003038. So that's our error. That's what they're asking for. Okay, let's look at the next part. Use your answers to part A and B to find an interval A to B such that A is less than or equal to f of 2.3 is less than or equal to B. All right, so we're supposed to use our answers to parts A and B. Well, in part A, we found that P3 of 2.3 was equal to 6.921. And then in part B, we found that our error is less than or equal to 0.003038. So what this error number means is that I can go 0.003 in either direction from this approximation, and my actual value of f of 2.3 will fall within that range. And that's what it's asking for right here. So f of 2.3 is somewhere in between my approximation minus my error and my approximation plus my error. So 6.291 minus 0.003038 and 6.921 plus 0.003038. And when you type those numbers into your calculator, you get that f of 2.3 is between 6.918 and 6.924. So that's the range of values that f of 2.3 would fall between if I used that third degree Taylor polynomial to approximate it. The actual value of f of 2.3 has to be between those two numbers. Okay, so on part D, could f of 2.3 equal 6.922? Explain why or why not. Well, yes, absolutely, because f of 2.3 falls in between these two numbers, and 6.922 falls in the interval found in part C. Could f of 2 equal 6.927? No, because 6.927 is not in this interval found in part C. So 6.927 is not in the interval found in part C. Now, on the AP exam, they will actually, it's common for them to ask you part D without asking parts B and C. So the way that sometimes they ask about the error is, could f of 2.3 equal this number? And so you have to go through parts B and C to answer the question, but they don't specifically ask you to do parts B and C. Okay, and we'll practice that. But for this example, I just wanted to take it out step by step by step. But just know that in the future and on the AP exam, they could do part A and then jump down to part D and just say, could f of 2.3 equal this number? Explain why or why not. But you would still have to go through finding the error, using the Lagrange error, and all that. Okay, next example. The third degree Maclaurin polynomial for f of x equals sine x is given by p of x equals x minus x cubed over 3 factorial. Use Taylor's theorem to find p3 of 0.1 minus f of 0.1. So, once again, it's an error problem. Taylor's theorem is the same as Lagrange. They're interchangeable. And this right here is just a fancy way of find the error in using this polynomial to approximate f of 0.1. All right, so before we kind of jump into this, let's make sure that we're clear on what all these parts of this formula are going to be. First, identify what your C is. Well, the fact that it's a Maclaurin polynomial and that these are just x and x cubed means that it's centered at x equals 0. So our C is 0. Now, the x that we use in the formula is the value that we're plugging into P to get our approximation. So P of 0.1 is the approximation, so the x value is 0.1. All right, so ultimately we're looking for big M, which would be the maximum of our next derivative. Now, if we used the third degree Taylor polynomial, then our error is going to be dealing with the fourth degree. So we're trying to find the maximum of the fourth derivative of x times x minus c to the fourth all over 4 factorial. So my first task is to find that maximum of my fourth derivative of f of x. Okay, well, we know that f of x is sine x, so f prime is going to equal cosine x. F double prime will equal negative sine x. The third derivative will equal negative cosine x. And my fourth derivative is back equal to sine x. So my task is to find the maximum of sine x on the interval from 0 to 0.1. All right, now, give me just a second here, and I'm going to make your life a lot easier. The whole point of this error was discovered a long time ago before you had these wonderful graphing calculators. So without a calculator, it would be really hard to find the maximum of the sine of x between 0 and 0.1. So what we're going to do is we're going to use a number that we know is bigger than the maximum of sine x between 0 and 0.1. And what we know about sine is that it's an oscillating function, and it fluctuates between y equals -1 and +1. So the maximum of the graph of sine x on its entire domain is 1. So for trig functions that are periodic, you can always use 1 in Lagrange error. So the graph of sine x actually looks like this. So the sine of 0.1 is just going to be a little bit more than 0. It's really not anywhere near 1. But what we can do is we can use 1 because we know that that's a bigger number. And if we're using a bigger number, then our error will always be less than what we're using. So the bottom line is that you can, if you're trying to find the maximum of sine or cosine on any interval, when you're using Lagrange error, then you can always use 1. The error, or the difference between my approximation at 0.1 and the actual value of f of 0.1, is going to equal the maximum, and we use the third degree here, so it's going to be the maximum of the fourth derivative, which in this case is 1, and then times the difference between x and c. And this is all absolute value, so I'm just going to take the bigger minus the smaller to the 4th power over 4 factorial. And that is your error. That's an acceptable error. Your error has to be smaller than that number. Without a calculator, or even, well, most of the time, if they don't let you use a calculator on this, this answer is perfectly acceptable. You may leave it your answer like this right here. Every once in a while they'll put a twist on it and make you simplify this just a little bit, but this is not that bad. 0.1 is the same thing as 1/10, and that's to the 4th power, and then divided by 4 factorial, and 4 factorial is 4 times 3 times 2 times 1, which is 24. All right. 1 over 10 to the 4th power would be 1 over 10,000. And then divided by 24 is the same thing as times 1 over 24. So your error is actually less than or equal to 1 over 240,000. You'll see in the next example what I'm talking about of having to simplify that fraction. But either the numbers will be nice like this, or you'll be able to use a calculator. Okay, let me make another just little comment about finding the maximum of a function on an interval. Let's say that your f of x equaled e to the x. And let's say that we use the 4th degree polynomial to make an approximation. And if we wanted to find the error in that approximation, then I would need to find, and let's say that we were centered at 0 and we were trying to find f of 0.1. We'll stay with 0.1. All right, so in order to find the error of using the 4th degree Taylor polynomial to find f of 0.1, then what we would need is the maximum of my 5th derivative on the interval between 0 and 0.1. And then I would have to do times 0.1 to the 5th power divided by 5 factorial. But the big part that is harder to find is the maximum of that 5th derivative. Well, my 5th derivative of e to the x is still e to the x. But e to the x is not a periodic trig function that whose maximum is never going to be greater than 1. So what you have to do is use what you know about e to the x. So e to the x looks like this and is always increasing. So this is where x equals 0, and then this is where x equals 0.1. So the maximum of this function on the interval from 0 to 0.1 is when x equals 0.1. So the maximum of my fifth derivative on the interval from 0 to 0.1 is going to equal e to the 0.1. So if your function is not a trig function, then it's going to be something that is either strictly increasing or strictly decreasing on that interval. So your maximum is going to occur at one of the endpoints, and you've just got to figure out which endpoint that is. That doesn't come up very often, but it was worth mentioning. Okay, let's look at the last example. Okay, so we've got a function that has derivatives of all orders. Once again, we're given the values of the derivatives at x equal 2. And then it tells us that the graph of f4 of x, the fourth derivative of f, on the interval between 2 and 3 is shown right here. Part A, find the third degree Taylor polynomial for p of x about x equals 2 for the function f. Okay, so this should be old hat by now. We take f of 2, which is 4, plus the first derivative at 2 is negative 1/3, times x minus 2. We're centered at x equal 2 because that's where we're given all of these derivatives. Okay, plus the second derivative, which is negative 1/5, times x minus 2 to the second power over 2 factorial, plus the third derivative times x minus 2 to the third power over 3 factorial. All right, and then part B, use your answer to part A to estimate the value of f of 2.8. Okay, so f of 2.8 is approximately equal to p of 2.8. And if you plug in a 2.8 everywhere you see an x in part A, then you get 3.706. All right, so A and B, easy, easy. All right, part C, use the information from the graph of the fourth derivative of x to show that f of 2.8 minus p of 2.8 is less than 1.25. Okay, so this is our error. It's asking us to find the error. And we're supposed to use this graph right here. Well, remember that our error, if we use the third degree, our error is all going to be fourth degree. So we need to find the maximum of my fourth derivative on the interval between 2 and 2.8. Well, how convenient that they gave us a graph of the fourth derivative between 2 and 3. All right, now here's the catch. We're really interested between 2 and 2.8. But we cannot make a good guess as to what that maximum, because the fourth derivative is increasing, our maximum is going to occur at x equals 2.8. But we cannot make a reasonable guess as to what that y value is. So you have to use what you know beyond a shadow of a doubt to be the maximum on this interval. Well, beyond a shadow of a doubt, I know that 7 is greater than any y value on the fourth derivative between 2 and 2.8. So that error is going to be less than or equal to 7 times the difference between where I'm centered and where I was approximating it. So 2.8 minus 2 is 0.8 to the fourth power over 4 factorial. Okay, so please do not guess that the fourth derivative at 2.8 is about 6.5. You cannot do that. You have to use what you know beyond a shadow of a doubt. And it's okay because we're just looking for a bound on this error. If this number is even a little bit bigger than what it should be, that's okay. I know that my error is going to be at least smaller than that. All right, well, if you type this into your calculator, you get 0.119. So that is less than 0.125. And that's all it was asking you to show. And this is just another way that they ask about error, is show that your error is smaller than some number. Whatever number they give you right here is going to be just a little bit bigger than what your error is. All right, that's it for today. See you tomorrow.